I'll talk to you. But don't they need to have lunch?
No, they already have lunch. We bring it at 12. Oh, the other guys? I'm sure he's bringing their pizza.
So you want to make the introduction?
Speaking to them? No, that's okay.
Good enough.
Yeah. How many do you have on time?
We also have an ambient mic.
It's iodine.
Oh, okay.
We got 3 people.
Very good. These are sites.
Site?
We have sites,
Oh.
so it's not people. So I thought like sometimes they get in a room and
everyone. So today I'm very happy to introduce one of our distinguished professors in the civil engineering department, Dr. Professor Youssef Hashash. And just a brief introduction to him is he's a professor of the civil and environmental engineering department, geotechs department branch. And he took his undergrad and graduate degrees from MIT. And today's talk is going to be about using discrete elements for modeling railroad ballast. So I'm happy to introduce him again, and then let's give him a round of applause before he starts his talk.
Okay. Well, thank you for the kind introduction and for having me here to share with you the work we have been doing. The work I'll be talking about is something we've been doing for 15 plus years, and it involves many colleagues, Professor Tutumler, Professor Gabusi, he's not here, you know him, and Unyan Park, plus a number of PhD students. I have lots of material I can talk about today. I will keep in mind the time so that you all are able to finish on time, and feel free to go back and forth and grab your pizzas. It's good pizza you have here. So, okay. So I'm going to talk about the overall broader issue of the simulation of granular materials. This is something you deal with here at ICT a lot. And then I'll talk about what the technique we are going to use for simulation of this material using the discrete element method. And we'll talk about the general concepts, BLOKS3D, which is our code for that, and the applications. Then I'm going to introduce you to an impulse-based discrete element method. And I'm going to tell you, if any of you have played Angry Birds before, you will see why this is important. It's all real work, okay? So when someone sees you playing that game again, you can refer to my talk about it. And we'll talk about some future work we're doing. Granular materials, you know a lot about them, composed of individual particles. They're all around us: powders, pills, soils, ballast layers as an example, which is, I'm going to refer to it a lot because this has been part of my interaction with Professor Tutumler on this. The material is not continuum, and it's the discrete nature of that material that controls its behavior, and it's the particle-to-particle interaction. We can approximate a continuum model of this material. We may find it useful sometimes, but there are times whereby the modeling of individual particles is going to be extremely helpful to us. We have no universal theory or model on the wide spectrum of scales, and we use continuum mechanics framework, finite element, and I use it a lot in my many geotechnical engineering applications, but it has some limited capabilities because it is phenomenological as opposed to capturing the underlying mechanisms, and it doesn't work very well when we deal with problems of large displacements and more so bifurcation. That is when we develop a shear plane in our granular material. That doesn't work as well for us. Also, how do we deal with a continuum framework when we are working with excavation and dumping, or something like pill handling or lunar rover mobility? There we really, the material sometimes behaves as a fluid and sometimes it behaves as a solid, and you cannot represent it readily with a continuum mechanics framework. So The discontinuum approach attempts to represent each particle individually and tries to understand to capture the interaction between these particles, and it's capable of capturing the complex behavior of granular materials, and this is mostly in the form of the discrete element method that is widely used. If some of you use PFC code, it is also a discrete element. So when it was proposed by Kundal and Strack in 1979, and it is by far the most widely used method, and it approximates particles as disks, spheres, or ellipsoids. And the way it works is it assumes these particles are rigid, mathematically straightforward. You have a mass spring damper system, and you do an explicit integration of second order equation of motion. And that's important because it becomes a dynamic system, and you are limited to very, very small time steps. It becomes computationally expensive. The other aspect of it is that you have to figure out when your particles are in contact or not. Visually, we can see it, but you need to do that mathematically when you're doing a simulation. So this is the type of simulation you do, is you have a collision, and based on the collision and the spring forces, you can estimate particle forces. And one of the issues you have to deal with when you are dealing with spherical particles is spin. That is, when you approximate a granular material, which is not spherical, by the way, by a spherical particle, you have to mathematically do something to prevent unrealistic spin in the particles. And then you have to do some motion update. I'm really not going to go through that. But you have a process of, this is the equation of motion, new forces, update contacts, velocities, forces, new forces, and then you update your equation of motion, and you continue that, and it is a stepwise process. You have a stability issue in the equation of motion, and that imposes on you very small time step. So if this is your physical experiment, this is this. If we put a spherical model, the problem you have is the particle will roll. If I have a polyhedral model, will more realistically represent this. And that really is the cornerstone of the work that we've been doing here at Illinois, is that we have our discrete element code that can represent the actual particle shape. And that makes a big difference in our ability to capture the underlying mechanisms that relate to the interaction of the particles. When you are dealing with spheres, you have to make so many approximations. You sometimes have to fuse spheres together. People have done that to capture, say, the shape of your particle. But from our basic understanding of granular material, we know that particle shape controls its behavior, in addition to, of course, the frictional properties. And therefore, the discrete element work we've done does that. Now, and so therefore, now instead of having to deal with contact between spheres, which is trivial mathematically to do, now I have to do contact between particles. How do I do this contact detection numerically? It becomes very expensive, and we spend a fair amount of effort to enhance the algorithms so that we can do this calculation quite fast. Kundal introduced in 1988 the concept of a common plane, whereby instead of looking at a particle-to-particle contact, you look at a particle-to-plane contact. Then these are some of the details of how we do that. No need to go through that, but it really simplifies the process for us. Nevertheless, when Kundal introduced this technique, it was iterative. That is, you had to iterate many times, do a search for many planes before you find that plane that bisects the space between two particles. And what we did is we introduced our own techniques for that. So the first generation, by the way, of the work that was done here at Illinois was led by Professor Gabusi and his PhD student Barboza. They developed a DM code, and there the contact detection didn't use the common plane because it was about the same time Kundal introduced it. It was in fact checking all the vertices relative to the other particle, and that was quite expensive, but nevertheless it was probably the first discrete element code that used non-spherical particles. And they did a number of simulations for a variety of problems, including dynamic problems and sand compaction. So that in that one, the contact detection was a very, very difficult job. Let's go. Then we have the second generation of BLOKS3D. This is where we did significant development. We had two different methods. One of the best one, the faster one, came later, called the shortest link method, which allowed us to fairly quickly compute that location of that common plane so that we can find the contact between the particles. And that significantly enhanced our ability to run simulations with a few thousand particles. We're still using the common plane as our contact detection method, and the shortest link, it's an iterative procedure, but we narrow the number of iterations relative to the original common plane, and it's about 10 times faster than the original common plane. So it's an order of magnitude faster. The more recent one is development we have is the third generation BLOK3D, whereby we are completely rewriting the software from the grounds up, and I will get into why this is important towards the end of my talk, because our objective is to run simulations with millions, if not tens of millions of particles on desktops. I don't have to go to Blue Waters, which is the supercomputer on campus. It's to allow me to do that. Why? Because we need that kind of capability so that we can run these on a fairly routine basis, these simulations. And I'll get into that. And of course, we have a more recent one, this impulse-based discrete element method, which allows us to run about 100 to 500 times faster than existing DEM capabilities. So we're focusing a lot on making things faster. So let's first start about how we develop our grain or particle geometry. This is a work in collaboration with Professor Tutumler, and I think, isn't there an image analyzer here? So been working closely with Professor Tutumler on characterizing those railroad ballast particles, and you can use it, in fact, for any type of particles. And we take those geometries and we put them into the library for discrete elements. So therefore, the shapes we have are more realistic. We did something actually interesting, is that eventually those idealized shape we had in the library of the discrete element code, we did a 3D printing of them. I have them in my office. I should have brought them here, sorry. But they're really pretty cool. So if you're back on campus sometime, feel free to drop by. And you can, of course, Professor Tutumler uses it for other aspects to define some F&E ratio and angularity indices, which are important in their own right, but also we use them for discrete element development for simulation of railroad ballast. This is an example of the library we have developed based on imaging that was done on the image analyzer here. And this is the library that we have, in fact, in our discrete element code that you can see, and you can select any particle you want from that as you develop your assembly of particles. We usually don't stick with one particle shape. We use an assortment of those, and we do usually a randomized selection of those so that you have a range of particle sizes, shapes as you would have in the field, and also a range of particle sizes that would be representative of the conditions that you would have in the field as well. Now, we've done many type of simulations. We've had did something with a caterpillar with a front end loader trying to move some piles of gravel. We have a triaxial simulation of this is for railroad ballast actually testing. Again, I think this large cell is somewhere here as well. I'm focusing mostly on things here just because I am here as well. The first thing we did, in fact, a while back, there was a series of experiments done by Professor Lade and his PhD student, whereby this is a sand. And so if you look at sand, and if you really want to represent each particle, you probably need tens of millions of particles, by the way, which we cannot computationally handle. So we, of course, used larger particle sizes approximations. But we wanted to see is that if I'm using these angular particles, do I capture underlying behavior of soil? He did a series of tests at 3 different confining pressures and at 3 different densities. And from a soil behavior point of view, this means that the behavior will range from a contractive behavior to a fairly strongly dilative behavior, depending on where I am. And what we did is we did a simulation. We only calibrated with one of these, and we only had to do 3 parameters: stiffness, friction angle, and damping, and to reproduce one test. And then we predictively looked at all of the other ones, and we were pretty surprised that actually we captured that behavior. We were able to move from a contractive to a dilative behavior simply by having the correct particle geometry and assembly. Those of you who do continuum modeling know that in order to have a soil constitutive model that will be able to capture that whole range of behavior, you have to have a very sophisticated model with 8, 10, 15 model parameters. You don't need to do that with your discrete element model, and this is an example of how we were able to capture these. Again, we used a single lab test to do the calibration and predict. I hate to use the term predictive. We computed the other 8 of them, and we did a very good job looking at the transition from a contractive to a dilative behavior. This is all documented in a published journal paper. What this tells us is that when we do things right, we capture the geometry, we capture the right, there actually we didn't even have the right particle shapes, sizes, I'm sorry, we had the particle shape. You can actually capture important mechanisms in granular material behavior. So reasonable, and my objective is sometime down the road when we significantly enhance our computational capabilities is to run a few million particles and look at this problem as well. In terms of ballast test, there was a lot of work done here, and what we used that to also look at how well our discrete element simulations. The nice thing about working with railroad ballast is we do not need to compromise on the particle size. We can represent the particle sizes. They're large enough, so this is good. Now, when the ballast becomes fouled and break up, well, we have other issues. We'll deal with them later on. But for that, we don't have a problem with that, and that's really great because we can have the right particles. In order to simulate the membrane, we have elements here. They are discrete elements, but they don't have forces in them. So it allows us to apply the confining pressure on those samples. We had to, in the loading in the lab, you do a continuous loading procedure. We adopted a stepwise procedure, and that is because we found that, in fact, there are no real rate effects for this type of material. And this is a simulation of how these things look like, the type of simulation we have. And let's see, the shapes don't look terribly bad. And then the computed stress strain curves look also reasonable. Notice that whether you're looking at the data or the DEM, you see jumps. And why do we have jumps a little bit in the data? Because you have particles, and as you shear, they start suddenly, sometimes you overcome the friction and they move. And that's why you have these jumps. The other thing we noticed that is important to understand the initial condition on the overall test result. Because how do we, the same way when you do sample preparation in the lab, numerically how we prepare the sample will in fact result in a cluster of data. So we found that a good number, you need to run 3 simulations to get a good average of the results. We also found out that there is really no effect of, and that was important for this type of test, whether you do rapid shear or slow shear, you get about the same result. So this is the one which shows that the strength test results are not sensitive to strain rate, and that was really good news for us because we could do this incremental loading procedure within our simulations without having to worry about these rate effects in the test. Another one was the shear box, and I think it's also here, the shear box. I'm not sure. That was done by one of Professor Tutumler's students, and we also repeated the simulations, and we get results that make sense and have the same trend. So there were some also field scale ballast settlement tests that were done, and we could also reproduce those in a DEM. This is your railroad tie, the tracks, and you're concerned about the settlements due to repeated loading, and we could do these simulations, and again, they gave reasonable estimates of those. The problem sometimes we have is if you have too many cycles, this becomes computationally very expensive. It can take a long time to do the simulation, and we haven't always done that. We had to do some extrapolation of the data. So this is some of settlement of estimation DEM and from the railroad, and so you can see actually they're not too far off. These are from DEM model simulation, and these are from the field measurements. So again, this is sort of ground truthing to see, does the data make sense? Now, we did not have to specially calibrate our experiments, our simulations for this. We simply use the same properties that we use in Triaxial Test, in the box shear test, and they gave us very nice estimates of settlements. So we consider it a reasonably reliable tool. And I always like to compare with real data to see how far off or how close I am. And they remain, of course, approximation. This is, again, showing a half section simulation of the particles in DEM. And then the procedure of how we, in fact, do this. So first, you have to develop your pile of granular material, then you have to compact it, and then you put your railroad tie there. So one thing that was really important for us as part of the collaboration with Professor Tutumler, but also broader interest, is how do we make this relatively sophisticated analysis tool accessible to our to a broader user base, not just engineers, the researchers that are doing. So we undertook an activity whereby we built a user interface for the software, specifically to guide the users through this process. This is the architecture of our user, of the software itself, and let's go through some basic elements, what we have. We wanted to have an interactive view so that you can see what you're working with, and then you can simulate a few typical problems. And this is, you start with, the first thing is you set up your project, file name, space of interest, your acceleration, and your grid space, just so that you can define the domain. And then you can select one of several problems. We wanted to have a few preset problems, specifically this one, because it was FRA, the Railroad Administration was actually funding this activity. So we made sure that there is a railroad problem there, but we had other problems like a triaxial cell, and also we had a box whereby you can open a side and you can see a flow of material. And the user can put in also membrane type of elements. It allows you to do that. And then it shows you the space within which you work, and then your objects are. And then you can define your grain size distribution to represent the particles. And based on that, the software will automatically adjust the sizes, scale the sizes of the particles, randomly select from a number of particle shapes that you have. You can say, okay, I want this, this, and this, for example, and then it will randomly mix them up for you as it develops the pile for you. And then the first thing you have to do is to develop that pile, and the way we do that is we rain that pile in. you drop those particles. Well, here we show spheres, but actually there's no spheres. We need to change that image in our software. Talks about how you locate your particles, and then from there you specify the gravity for each of the material, and then you now put in your contact properties, which control the behavior, stiffness, friction angle, and damping. And with that, you tell it what kind of simulation, time step, and then you run simulations and complete them. So it takes you through this stepwise process. Then you'll see lots of these numbers as it's cycling through. And we have a number of outputs. So this one, for example, is pouring of particles and gives you this. So you can simulate a triaxial cell test. This is for a railroad ballast. And let's see. No, let's go back. Continue this before I get into this. Well, we're getting into this. I want to spend some time on that. Currently, we have the software has been made available to the sponsors, and they're working with it. This is the first time we ever release it outside of our laboratories. Hopefully, they like it, and we'll see. I'm still waiting for feedback. We spent quite a bit of time back and forth to make sure that the software runs. And I do not know to what extent you're familiar with deployment of software. It is not a trivial task. It's a lot of work to get a software that can be used by somebody other than the original developer. And I'll talk about software development in a little bit way. So now let me shift and talk about a bigger problem that we have. So I've shown you all this, and I can tell you, oh yeah, we've done all this great work, and we can run the simulations very fast. They're not fast enough. That's the bottom line. If I need to run tens of millions of particles, I need a high-end supercomputer, like Blue Waters or something like that. Most of us have a PC. We may have a box, maybe it has 30 cores or something. But I don't have access to these. So we need to make sure, in order, if we really, really want our software to be used in routine engineering design, we need to make the calculation time much faster. Finite element is widely used because it's fast. It runs within a reasonable amount of time. This one takes a long time. So we spend a lot of time looking at how can we speed things up. So here I'm talking about a contrast of two things. One is computational science. Our focus in computational science on simulation fidelity. How good, we're sometimes are trying to be precise without being accurate, or we're just for the sake of precision without any real meaning, in fact. They are DMs, computationally expensive, run slowly. Second order time integration, I have to have a very small time step. Contact forces are acceleration-based dynamics, and I need actually double precision, by the way, in my calculations. All of that was going to slow you down. While in computer graphics, and many of us, you have your phone, you can play your game. The focus on speed, stability, and physical plausibility. I mean, it looks pretty realistic, right? Good enough type of thing. These are physics engine, fast, stable, with relaxed accuracy. They accept some approximation. They do a first order integration of time, large time step, and collision impulse. It's velocity-based dynamics. They run very fast. This is Toy Story. If you didn't, I'm sure you knew it. But you don't get forces. And as engineers, we love forces, right? We need forces. We need to know what kind of stress we have to deal with. So you pay a heavy price if you use these, but they're incredibly fast. I could never come up with something this fast. So one day, my daughter was playing Angry Birds. Of course, I kind of really don't like my kids to play Angry Birds and games, because I think it's a waste of time. But I was watching her, and I'm looking at this. I mean, look at these. These are particles, right? These are objects. even if I take my DEM code with the best optimization, etc., I cannot run it this fast, okay? I cannot run my simulations as fast as I see these, okay? See, these are all particles, right? And they are polyhedral particles. It's not even spherical that I can say, oh, they're doing them. So I was wondering, what could they have done that's faster? Of course, we saw with Toy Stories, but you hear about they have these huge computers, they run simulations, but this is something that runs on your iPad, on your mobile phone. So why is it? So I came back and went to my student Sanjay Lee, and I said, Sanjay, we got to look into this. And I thought it's some sort of a secret code. Well, it turns out no. All computer games, or most of them, use an underlying physics engine called Box3D, which is open source, right? And it's used by many, many, many video games. There are other, if you have some other favorite video games, like there's one with a bunny, so they use that. They use this collision impulse, and no springs between particles, and they can go for very large time steps, and they can do single precision implementation. Everything that I cannot do with regular DEM. I cannot do any of these things. I cannot go for large time step, single precision. So what we decided is we said, okay, well, the advantage is fast, numerically stable with large time step, and looks plausible. And honestly, to think that we can exactly know the position of a particle in an assembly is we have a phenomenon of chaos, etc. So what is missing in impulse method? No force contact at all. We don't have the forces. But this is critical information for us as engineers. So, and that's actually the innovation we have, is we developed a technique to retrieve contact forces from collision impulse using this basic principle. And we call this method impulse-based discrete element method, IDEM. And the little I, we didn't do it by accident. There's lots of I things we have in our technology world. So we thought IDEM would look pretty cool. It's a good, so we coined that name, IDEM. Sanjay received a number of awards for this, introducing this technique at conferences. And so let's look at how, well, of course, if you're interested in the mathematics, you're not going to understand it by looking at it here. We have a journal paper. It's available, and the details on that. But there are a lot of analogies between DM and IDEM, except that you are integrating a velocity equation as opposed to double integrating an acceleration equation. And let's see. There are a bunch of things that you have to find. Instead of damping, you have this thing called coefficient of restitution that you have to work with. Okay, stuck on this equation. Okay, and this is talking about how we do these contact detection between the particles, but let's go to, so what we have done is we've shown the analog between the IDEM and DM. This is a classical DEM calculation versus the impulse-based DEM calculation. There are certain things we do in DEM we don't do in IDEM, and vice versa. What that means actually is that we were able to quickly implement IDEM in our software. We didn't have to produce a separate program. It's the same program because there are many things we use in common, such as contact detection, so forth, so on and so forth. The key difference is that I can work with much larger time steps than IDEM. And one thing about IDEM is that I can, in fact, finish the simulation completely and then compute forces. They are not essential for the computational cycle, while in discrete element, they are essential. I need the force calculation to be able to do my analysis. This is explaining how we came up with the idea of force calculation and inverting for it. And it's it can be, the way it is that the force can be approximated. We can retrieve the contact force from a collision impulse model. It's an approximation, which works very well for us. And we did a whole bunch of things as well to be able to add up the forces as the collision happens, as the particles move back and forth. And we were able to, okay, so We implemented the IDM algorithm within BLOK3D, so now we call that iBLOK3D. And we're going to show you the simulation fidelity and the computational efficiency. And that's important. Fidelity in terms of configuration and contact forces, and computational efficiency, code speed, and memory usage. And that's important, because remember, if you want to go for millions of particles, you then, the RAM usage will be quite a bit. So we did a number of simulations. We did, and the way we looked at it is we looked at the time step of IDM of DEM. We have 500, 5,000, 50,000, and 500,000 particles. I could never run 500,000 particles on a PC, okay, with polyhedral particles. That's not feasible for us. But IDEM we could. And the time step is 1, 10, 50, 100, 200, 500. If you can do 500 times the time step, it's about 500 times faster. Well, it's not exactly, there's a little bit. And then we have different particle sizes, and this is the time step for the discrete element model. And these are some of the parameters we used, don't need to worry about it. And also notice that with DEM, I only could run 500, 5,000 within a reasonable time. 50,000, 500,000, I'll give you estimates of how much time it would have taken us to do them on the same computer platform. But here we were able to go with single precision computation. With DEM, you cannot go. It's needed for the accuracy because you're doing a second order integration of your equation of motion. This is DEM, that's the simulation, and this is the IDEM. That's how when we start our simulation, 500 particles, same time step. When you have the same, and this is this is when we're simply forming the pile of sand, 10 times, 50 times, 100 times. You can see it's actually going smaller because the reason is if you now move too big of a time step, you may end up missing some of the collision. So what will control the time step is the distance between any particles. Otherwise, you'll physically have one particle go past another. So that's the limitation is physical. It's no longer numerical, and that's very important for us. Numerical is I have to think of it. These two particles, I have to go tuk, 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 before I hit this particle. In IDM, I can just go this way, go directly without having to go through those intermediate steps. So this is showing the configuration. This is, let's think of the DEM if we want to consider the correct solution. And this is showing with 1, 10, 50, 100, 100, and 500. You can see that at 50 time step, you're still getting a reasonable pile. Even at 100 time step, it's a pretty reasonable size of pile. It's when we go 500, the particles, there's too much overlap. And if you look closely here, you'll see that overlap. But nevertheless, by the way, I could never run a DEM analysis with 500 time step larger. It's numerically unstable. Here, I actually get a stable solution. Now, then we look at the flow, particle flow. This is the blue background behind shows us, let's call it the DEM, for us is the reference solution, if we want to call it. And the front one shows what we have with the IDEM, this much faster. If this is 10 times, you can see doing well. This is an order of magnitude. This is 50 times, 100 times. I still have a pretty reasonable. I can go 100 times faster and still get pretty reasonable shape. Remember the whole issue of physically plausible. 500, well, we are paying a price, but you will be surprised that forces are not bad even for 500. So this is just showing us how that even when we can still have an approximately bad solution, but it's still I can get an answer as opposed to no answer with DEM. And if you look at the forces, we get very good estimate of the forces, really, really good estimate. This is 1, 10, 100, and then even 500. And by the way, this is 100, and this is all double precision, and then single precision, which will save me memory in my calculation. 500, it's starting to depart, of course, but this is normal force, and then the shear forces. Shear forces are not terrible, but even up to 100, I mean, think of it as if I'm giving you a computer that is 100 times faster. That's really what you have that way. So this is the computation of forces. This is CPU time, and you can see with double precision, I mean, we're going from 373 seconds, I can run it with 4 seconds, sorry, 5 seconds. Same simulation. This is the time step of 100 times, I can go 80 times faster. Now this is worth it, okay? And let's see why we say it's worth it, because okay. Oh, I went too fast. Now the 500,000 particle simulation. Now that I can run on my PC, and you can go for much smaller particle sizes. And we did not have a DEM solution for the problem, okay? Because we did not, it would have taken us, I think, a year, by the way, to complete the simulation on the PC. But this one we ran it, I think the statistics are coming up. So you can see how we have very, very small particles now, and that's important. If we want to do simulation of real granular material, we may want, other than say railroad ballast, something smaller. Now we are getting closer to being able to do that. And the speed up we have, we can go 200 times step, 500 times step. The DEM, we didn't do the calculation, we didn't actually do the simulation, but we estimated it will take us 280 days to do the simulation. We ran it in 4 days, between 2 and 4 days. That's how long it took us. Big difference, you know, 2 to 4 days I can run it, I can do many simulations. I can't keep on waiting a year every time to do that. Okay, so let me go to the conclusion, and we'll have some discussion on this. Discrete element is the most suitable way to simulate complex behavior of granular material. We have been developing BLOKS3D for 20 years, been successfully utilized in many applications. The Ballast BLOKS3D, this is the one with the user interface, now allows for track performance evaluation, and it's being, let's call it alpha or beta tested. IDM, impulse-based DM, will provide us with, I think, a paradigm shift in our ability to do particulate material simulation in engineering, because we can run 100 times faster or more. Where are we going with this? I mentioned to you a little bit about 3D printing, but really the ones that I'm focused on now is I really want to be able to run 1 million, 2 million, 10 million particle assemblies on a PC, so that if some of you, for your application, decided you want to do a DEM simulation, you can actually do that. And we are actually making some good progress. Do you know what GPUs are? Graphical processing units. They are now becoming widely available on personal PCs, on laptops, desktops, and accessible workstations. And we are hoping for about 1,000 times speed up or so. In one of the things we're doing now, and Unyan Park, he's the PhD student working on this, is we're completely rewriting the code software from the ground up. And we're already seeing a difference in how we manage memory. Instead of, for some simulation, using 200 megabytes, we only need 20 megabytes of RAM. Well, why is that important? That will allow me to run larger assemblies more efficiently, which will make the entire simulation platform far more accessible. I'm not going to say it will be as accessible as finite element, but it will be far closer to our routine daily or research use, as opposed to where it is right now, whereby we're either stuck with spherical particles, which do not represent the geometry, or we are limited to very slow simulation. So stay tuned, and I think I am done. Thank you very much. And any questions? Yes. Yes.
So I have a couple of questions. The first one is, like, have you ever tried to do parallel processing in your calculations? For example, in finite element stiffness matrix and force matrix are different, so you can send them the different code. Have you ever tried such a things on?
Yes, we have. And we've done it many times over, and we're continuing to do it. So there are parts of the code that are very much ideally suited for parallel processing because you need to do contact detection for, say, 1,000 particles, and you can do that in parallel. But remember, you have to send the data and then collect it back. You're still going to be limited because of the time step. We saw some acceleration, but not enough, in my opinion. So we used, I think it at the time OpenMP. I'm trying to remember what we used, but right now we are going for an OpenMP implementation because GPUs is ideal for parallelization, right? And that's what we're working. We've done it before, but it wasn't fast enough. You need to be using very large assemblies of particles. And at the time, we only had access to these big platforms, computing platforms, supercomputers. And those, you put your job on the queue, and sometimes you have to wait a few weeks before they execute it. Well, by then, I would have been done on my PC. But I want to do the parallelization on my PC. And nowadays, we have widely available multi-core machine. Like in my office, in my student's office, I have a couple of, say, 32-core machines, right? And you can do multi-threading, all that stuff. So we're fully working on that right now to do it, and through the complete rewrite of the software. That's another thing, is that if you keep a legacy software, which is started about 18 years ago, there are many, many new things we learned about in software architecture that we're working. So yes. Second question?
Yeah, so like I missed it, like kind of beginning of the presentation, but for example, are you able to think other like material in your simulation? For example, water. What if like
what is it?
Water, for example. What if the rain, like for example, aggregate in another, like flowing in another environment other than air?
Right. So the question is about incorporating something like a fluid, like moisture or either partially saturated or saturated material. No, I have not done that yet, because up till now, discrete element calculation with polyhedral particles is computationally very expensive, and adding to it a fluid flow or fluid interaction will make it even more expensive. And part of my objective now is to, in terms of rewrite and re-implementation, complete rethinking of the architecture on multi-core machines, is to be able to move to that part next. Yeah, question?
I have last one.
Can I get your
sure.
colleague, and then we'll come back to this? Actually, your colleague and then another one of your colleagues.
Okay.
Yes.
First of all, thank you for coming.
Thank you for having me.
My question is, I was wondering if there's a threshold in the size of the particles where you can see that the continuum solution is equivalent to the DEM solution, so you don't have to go through the trouble of doing the DEM.
Can I rephrase your question, if I may? It's not the particle size threshold that will change the problem from being suitable more for a continuum versus a DEM. It's more of the nature of the problem that I'm working with. If I have a problem where I have a flow of the material, I cannot simulate that well with a finite element. I mean, of course, you can do some sort of maybe a Stokes flow type of meshless methods or something like that. But you need to actually represent, the DEM is of course superior in that, because you're representing that. Now if the material is not moving, that is, there's not significant particle movement relative to relative particle movement, then actually a continuum simulation is quite okay, such as a loading, for example. But even for railroad, when you have an issue of, you have to start looking at issues of crushing of particles, for say the railroad ballast, understanding the interaction of particles becomes more important. Problems where you have low stresses, which is surface type, I think DM will probably give you some additional insights compared to the continuum. I'm not advocating we abandon that. In fact, ultimately, we want to have is both finite element and DM together, whereby you can switch from one to the other depending on the problem you're working with. Yes?
I have a question like this, that is this statement true that the model intrinsically is highly time dependent? So.
What do you mean by that?
Because you told that this time increment is really related to the distance between particles. So, and distance, this is really dynamic, so they are moving and the distance may really change during some complicated happening. So then if that time increment is a function of this distance, so it may change. So still we need to have a small time increment for.
Sure. But that time increment is still much, much larger. This is with the IDM compared to the time step I would have to use if I were doing the DEM, discrete element modeling. That time step is so tiny because of the stability requirement of the integration. So there are two different time steps, and I might have confused you with them. So let's take the traditional discrete element modeling that people do. There's a very small time step. That time step is an issue of time stability. It has nothing to do necessarily with the contact. Is that the solution becomes unstable if you go based on the spring stiffness. And if you're interested, I can send you equations to show you how that is controlled. So it's based on the dynamics of the problem. You have, in its explicit integration, you're limited by that time step. And that time step is a fraction of the time step required for two particles to collide, for example. Okay? While in IDEM, I can work with that larger time step. With the IDEM now or with the DM? For IDEM, we're still working on that. This is a fairly new technique, 3 years old, and we're still looking into how best to help the user select a good time step. Like with any new technique, trying to figure it out. We found actually we can go with very large time steps. The solution will not blow up. It'll just become realistic physically, as you can see the particles are overlapping too much. It becomes physically implausible. So.
Say there are some results.
Well, no, the user needs to look at so definitely the user needs to look at whatever you're using, the user needs to look at the results and judge if they make sense or not. Okay, 2 other questions. Sure.
Should be determined.
So now the particles are homogeneous, they all have the same material properties?
Yes.
So it's not that, for example, different modulus for different particles?
You could, okay, so the particles themselves, as we represent them here, are rigid particles. The deformability comes, of course, from particle movement, but also that spring stiffness. Well, actually, we had a spring stiffness in DM, but IDM is not this impulse collision, this coefficient of restitution. In the future, we don't see any reason why not being able to change that. But see, then you have to think about it this way. You will have one type of material will be this, and another type of material will have that. But then when I have a particle from one material interacting with particle of another material, I have to have a different type of contact as well, properties as well. There is nothing that will stop us from implementing this. It's all feasible, okay? But we just don't have it implemented. It's, again, part of my stepwise approach to solving what I consider the highest priority challenges in these, and then go to the next ones. So I am a big believer in accelerating our codes, complete rewriting, and because we have actually, those of you who may know me, I have another software that's also widely used, and we were able to achieve a 10 to 100 times speed up through simply changing the architecture of our code. Turns out that as engineers, we don't know how to write software. Okay, it's as simple as that. And we had to work a lot with people in computer science. My students had to take courses in computer science, and you cannot imagine the difference in the efficiency of the software. It is unbelievable. I guess that's why they make so much money.
We had a question online.
Oh, okay. Can we take the question online? Is that okay?
How do you address the breakage of the particles?
That's an excellent question. So there are 2 ways you can address the breakage of the particles. You can a priori fuse the two particles and have a sort of a cohesion. And when that stress is, you reach a critical stress that will initiate a fracture, you can break up the particles. There is another way whereby you could inherently then use some type of a fracture initiation criteria to initiate a crack, and then you change the geometry of the, you take one particle and you split it. Do I have those implemented? Not yet. In fact, I was talking to a colleague of mine about writing a proposal about it, and if someone wants to fund it, let me know. But yes, we are actually, is there any more questions online? Okay, very good. So we have one question left here and one question left here. So you had one more.
Disappeared. So no more questions?
None of them. I have that question.
Oh, I'm sorry.
Yeah, no.
Okay.
So another thing. So you are going the way that you showed that to put. I mean, how do you design the mixture? It's just randomly pouring these particles on each other, or no? You should go and make these particles.
No, you have a choice. You can do. But the way I showed you those ones, we have a grain size distribution. We randomly generate those particles to fit that grain size distribution, and we drop them. As if, sometimes in the lab when you're trying to put in a sample, you drop it and then you compact it. That's what we do. No, it's too painful to do that. So you just imagine trying to put, and also fit them. They have to, no, we literally let a simulation whereby the particles drop and then we compact them. In fact, for the large triaxial here, how here you put a layer and then you compact it, then another. We do the same thing numerically, the same procedure.
So let's thank Professor. Oh, you another question?
No.
Okay, let's thank Professor Hashash with the round.